Hi everyone and welcome to discussion 11. So to start off, some announcements. Written homework 4 is due Wednesday, December 2nd, and then project 5, which is on machine learning, is due Friday, December 4th. So both of them are due the last week of instruction, so the week after Thanksgiving break. And then today's focuses for our worksheet will essentially just be neural networks, and we'll specifically talk about gradient descent more and about how computation graphs are used and how to interpret them. So in that case, let's just directly dive into a quick mini lecture on neural networks. So let me actually move this up a line. Cool. So the general motivation for neural networks, so the motivation is that most problems are nonlinear. So since most problems are nonlinear, we need another way to be able to represent different functions and equations versus just like our normal perceptrons or linear regression. And that is where neural networks come into play. So essentially with neural networks, we can kind of model these more complex functions by adding nonlinearities in certain layers. So that's why this is this whole idea of what we call a universal function approximator. And what that means is it's a two-layer neural network. So I'm just going to abbreviate neural network as NN with sufficient neurons can represent any continuous function to any accuracy. So as long as we have a sufficient number of neurons, which we'll kind of gauge what that means more in the second problem on this worksheet, and the neural network is two-layer, then we can represent any function, no matter what it is. So we will kind of see this in play in the problems on this worksheet. But prior to that, I kind of wanted to point out some other things regarding neural networks. One was the nonlinearity functions. So these nonlinearity functions are what makes neural networks so powerful because it allows you to kind of interpret something more than just a linear function. And how you do that is by applying these nonlinearity on some different layers. So the main ones we are going to deal with are sigmoid, and then for a sigmoid function, we essentially have the sigmoid of x is equal to 1 over 1 plus e to the negative x. And how that looks like on a graph is if you just have this and this is 0, then the function graph will look like that. So that's one of the main options, and then the other main option is what we call ReLU. So ReLU is a piecewise function. So we have like f of x is equal to 0 if x is less than 0, and then x if x is greater than or equal to 0. And then how that looks on a graph where this is 0 is it kind of has this L shape where it's 0 and then goes up. So these are going to be your two main nonlinearity functions, or what we call step functions, that you are going to see and deal with the most. And then one more thing is that I want to talk about is what we call gradient descent. And this is a process for updating your weights so that you can get the best weights as possible in order to get the most accurate predictions. And because of that, the two main steps are, first, you need to calculate the gradient. So calculate the gradient. And just kind of some key tips you want to remember is calculating a gradient is that you want to use chain rule and the computation graphs. Because using these two factors allow your calculation to be much easier, so that you don't just end up like taking the derivative of this really long function and then trying to find all the values. Because it essentially breaks it up into small points, and then you can find the derivative of each subpart and then multiply them all together by chain rule. Cool. And then the second step is actually update along the gradient. So specifically, the update usually looks like, if you have WI, then you want to update it to be WI minus the size of your step times the gradient. So essentially you are subtracting your gradient from all your weights. And that's because we are doing gradient descent. So I believe in lecture you also talk about something called gradient ascent, and the only difference is that instead of subtracting your gradient, you would be adding your gradient. Cool. So now that we've kind of touched on some brief ideas regarding neural networks, let's just dive into the problem. So for this first problem, we have this classifier, and we are using it to classify some data, and each of the n samples consists of a feature vector, and it's a label of y that's either 0 or 1. So the classifier we are using is just called logistic regression, and here are the formulas for it. And notice that this is called h of x, and yeah, and then x of x is e of x, and we learn a certain weight. Cool. So now we have this loss function down here, and we want to be able to minimize this loss function. So in order to do that, we need to take the derivative and then find when it is like a local minimum versus a local maximum, and then update accordingly. So that's why in step A, they ask us to find the derivative of the loss in respect to each weight, so in respect to WI. So cool, so let's just dive into the math for that. So we have our loss function right here. So we can get the derivative. Let me just start writing it out. So we have dl of dwi, and then that will be equal to, I'm just going to keep the negative sign. Okay, so the first term we have is y natural log of h of x. So what we can do is that we can use chain rule. So notice that we don't need product rule for this, because we are taking the derivative with respect to w of I, and y does not include w of I. Only h of x does, because we can see that with this formula up here. It takes in the inputs of all the sums of the weights times each x parameter. So that means here, just by chain rule, we just have y like a constant over h of x, because that's the derivative of the natural log, and then we want to multiply by h prime of x, but we don't know exactly what that is yet, or I'm going to keep it as this variable because I don't want to directly write out the derivative for this portion yet. Cool. And then we can also need to do another kind of step of chain rule, which is that in the h of x function, it takes in wi xi. So that means if we're taking the derivative in respect to wi, we also need to multiply by xi in order to account for that extra argument input and to fully complete chain rule. Cool. So then that is the first term. Now we got to do the same with the second term. So we have plus. We kind of have the same pattern of having 1 minus y on top, and then 1 minus h of x in the denominator. And then we need to multiply by h prime of x. Sorry. Yes, so we would multiply by h prime of x, and then we would also have an additional xi out here for the same reason. And then one thing I'm missing, I think, is a negative, because in this part, we're trying to find the derivative of 1 minus h of x for chain rule, so we would actually end up having negative h of x, so that means this would turn into a negative sign. And then, yeah, so that is the first step of taking the derivative. And then now, we want to kind of simplify this more. And notice that we got a hint, specifically this line right here, where it kind of tells you a way to simplify the derivative of s prime of the function. And notice that h prime of x is equal to s prime of the summation of I, wi, xi. And I am just getting that directly from the square right here. So then based on that, I can substitute that in. So I would end up getting derivative of the loss with respect to the weight will be equal to negative. So this stays the same, but now I want to substitute it to be h of x, and then times 1 minus h of x, and then so we still have the xi, and then we do the same thing over here. So we have h of x, and then 1 minus h of x, and then we still have the xi. And then we can continue just simplifying this. So we have that these two cancel out, so we just have xi y times 1 minus h of x. And then here we have the other two that cancels out, so then we have minus h of x times xi, and then times 1 minus y. And then we can kind of simplify this even more. Negative xi y minus y h of x minus h of x xi, and then plus h of x xi y. So then based on that, these two cancel out, and then we will end up getting that the derivative of the loss with respect to the weight will be equal to negative x I times y. Let me rewrite that. Times y, and then minus h of x. So this will be our derivative and also our answer for part A. Cool. So now we've done the first step on gradient descent, which is calculating what the derivative would be. And just to kind of reiterate, we use chain rule, which is a very important technique to remember. Cool. So then now in part B, we want to actually write out what the gradient descent update would be, specifically with our step size n. And this essentially represents the second step of gradient descent. So just kind of going off of our previous format, we would be updating the weight, so Wi. And how we update it is we take our current weight and we want to subtract the step size, which here is n, times our gradient. So times dl dwi. So then we already found our gradient in subpart A, so we can directly plug that in and get wi is going to be updated to wi minus n. And then I'm just going to distribute the negative, so it becomes plus xi times y minus h of x. And then this will be our update. And then that is what we would use in gradient descent. And now we have finished number 1. Cool. So then let's go on to number 2, which is focus on neural network representation. So throughout this problem, we are going to be given a computation graph. And then for each computation graph, we want to see which of these 8 graphs can be represented, or these 8 functions can be represented. And we want to also back that up with the specific weight parameters that we would input to get those functions. So just kind of going through and getting to know these functions first. So we have 2 of x, so just a linear function. And then we have 4x minus 5, so a linear function but shifted. So that's also what we call an affine function. And then we have a situation that's kind of like ReLU, where it's 0 in one case, but an actual line in the other case, and then kind of the flip of that. And then we also have flipped over the x-axis now. And then we have one where there are now 3 segments involved. And then we have a log of x, and also 3 segments, but now we have 2 diagonal segments instead. Cool. So those are generally the 8 functions we are looking for. And yeah, now let's just try number 1 to kind of get a feel for this problem. So here we have the first one. So consider that for this graph, or for this computation graph, we just are taking in a weight and a scalar, and the output is just going to be wx. So just multiplying the weight to the input. So which of the functions can be represented from this graph? Cool. So we know that all the functions that can be representative have to be of this f of xw is equal to w of x form. So it has to be a constant times x. And if we look back up here, the only function that is like that is the first function, 2x, because all the other ones are at least shifted in some way and aren't just normal linear functions. So that means for 1, the only function that works is option 1, and we specifically do it when w is equal to 2, because option 1 is for 2x. So that is the only one possible for this computation graph. Cool. Now let's look at number 2. So now we have an additional b, or bias that's going in, that we can now shift the linear function so that it no longer has to go through the origin. So instead, our result will now be able to be wx plus b. So kind of just like any affine function. So what we can do is we can kind of look back up and see that our main functions that are like that are a and b. All the ones have some other split or kind of an additional layer on top of that. So based on that, the functions that we can represent are going to be option A. Sorry, earlier this is supposed to be A. The options are numbered by letters instead of by numbers. Cool. So then here we have option A, and then we still want W to be 2 to get that 2x, but now we want B to be equal to 0 because we are not shifting that function. And then the other option that works is option B, and then we want option B to be, sorry, I also include the options on the right side so it's easier to look at, but we want option B to have W equal to 4, and then B is equal to -5 to get the -5 bias shift. And then this is our solution for 2. Cool. And then now let's move on to 3. So 3, now we are actually adding a nonlinearity. So we are adding this ReLU square after we get an FI function. So now we need to consider, what does this ReLU do? Well, we remember from the mini lecture, a ReLU essentially has this kind of shape where anything that's less than 0 will be flat, and then anything greater will be like the actual function. So we can kind of look for this like slanted L shape in the graphs, and ReLU should be able to represent that because we could find the appropriate way to either like shift them or flip them if necessary. So if we just look back up, we can see that the two that look like that are C and then D, which is just the same thing but flipped. So the negative, you can put in the negative affine function and then put it into ReLU. So that means for part 3, the ones that work are option C, where we would want W to be equal to 2, and then B to be equal to -5, and then option D, where we'd want the values to be the negative, so -2, and then we still are shifting by -5. But the weight is negative because we want to do the flip so that when you ReLU, you get the opposite. Cool. So then these are the two options that are possible with this computation graph. And then now let's move on to the fourth one. So now we no longer have a nonlinearity, but instead we kind of have 2 layers because we have 2 different nodes that are consecutive, and they are both affine nodes because they both have a weight and then a bias. So something to remember is that if you don't add any nonlinearity, no matter how many nodes you have, you will always end up being to only represent linear or affine functions, because it's like even if you have multiple affine nodes together, you can still only represent an affine function. You just need to update your like exact parameters accordingly. But since you are still not introducing any nonlinearity, those nonlinear functions are still not available to you. So kind of based on that, that means that this computation graph can only represent the same functions as the number 2 could. So the one where we only had one affine node. So that means we can only do A and B. So let me write that down. So we can only do option A and option B. But the difference is going to be what we assign the weights to be, because now we have to consider the other weights as well. So to keep it simple, for the option A, it was just getting 2x, so we can just have W1 equal to 2 and B1 equal to 0. And then we already have 2x, so we can just kind of continue that value through by having W2 equal to 1. So you just do 1 times 2, which is still 2. And then still having a bias of 0 so it doesn't get shifted. And then for option B, we wanted to be able to get it to be 4x minus 5, as we see on the right side. So a way we can do that is to have W1 be equal to 4, and then have W2 b1 equal to 1. So then right now we have 4x plus 1 as the h in this function, so right there. But then now we want to be able to scale it more, so we can have w2 equal to 1 so that we keep the 4, but then update b2 appropriately to be -5. Sorry, I actually messed up on this, and b1 should just be 0. So essentially we are just taking the first node and doing the kind of multiplication scaling with that node, and then we are using the second node to actually do the bias shift. So these are examples and kind of evidence that option A and B work. Cool. So then now let's look at 5. So 5 now still has those two affine nodes, but in the middle we have an added ReLU node. So we are adding some more kind of non-linearity involved, and in comparison to 3, which just had the one affine node and the ReLU node, we now have 2 layers. So with that, we have more flexibility that after you do ReLU, you can still flip the ReLU functions over, for example, the x-axis, so or like rotate it in any way. So kind of based on that, if we just look back at the different graphs we have, that means everything that was attainable with option 3, so C and D is still attainable because with the second affine node, we can just not do anything with it. But then that means now E is also attainable because that is just a ReLU but flipped or rotated 180 degrees. Or sorry, I mean flipped over the x-axis. So yeah, so then based on that, the options that are possible, we have option C, option D, and option E. And let's try to figure out the parameters we would have for it. So for C, which we just have the function of 2x minus 5 and then 0, otherwise we would want to have w1 is equal to 2, b1 is equal to -5. So to get the actual function of 2x minus 5, but then we would do the ReLU but still want to shift it, so we would have w2 to 1 and b2 equal to 0. And you can kind of just reason through and try out different cases to find these exact weightings, but in terms of the weightings for D and E, it will just be w1 is equal to -2, b1 is equal to -5, w2 is equal to 1, b2 is equal to 0, and then for E, it will be w1 is equal to 1, b1 is equal to -2, and then w2 -1, and b2 is equal to 1. So these 3 are the 3 options that work with this computation graph. And then let's look at 6 now. So now we have the similar thing of affine node and then the nonlinear ReLU node, but we have it multiple times, so it ends up having like 3 layers in our network. And now if we look at this, we can see what functions it can be represented. So if we just look at 6 versus 5, we see that it is essentially 5 but with like an added ReLU and an added affine node. So based on that, we know that 6 should be able to represent anything that 5 can be. So we already know that it can represent option C, option D, and option E. But the question now is whether it can represent anything else, and let's look at our graphs to see. So if we look at option F, for example, we see that it kind of mirrors having 2 ReLU functions because there's 2 flat portions. And then, yeah, so that means we only have one portion that is actual function, while the other ones are like being cut off by a nonlinear function like ReLU. So that kind of indicates that F should also work. And that is actually true. So we would want, or essentially to our list, we can also go through and find the exact weights for it. It will be kind of like a lot of trying out different numbers, so I'm going to skip that. But intuition wise, you should be able to kind of see how with ReLU you are cutting out certain parts of the graph and kind of making them a flat line. And earlier when we only had one ReLU, we can only make one kind of end of the graph flat. But now that we have two, then we can do it at different points of the graph and kind of have different flat components, which is why option F is now possible. So that means these four options are all possible for part 6. And then now going to part 7. So we have gone back to affine nodes, but now instead of just having one node per layer, we have 2 nodes, specifically in this first layer right here. So we want to see if this affects anything. But remember, here we still don't have any nonlinear nodes. There aren't any ReLU nodes. So even though we have like more nodes per layer or we have more layers, we are still only able to represent affine functions. There is no nonlinearity present that allows us to represent more complex functions. So that's why, in this case, kind of similar to question 4, I believe, with just 2 affine nodes, we can still only represent option A and option B, because those are the only 2 nodes that don't have any nonlinear components. And then same thing for the exact weights, you can kind of plug in and see, but it will be quite similar to the weights for part 4. And then last part is part 8. So we still have the situation where we have 2 layers, and the first layer has 2 nodes, but now we also have the added ReLU node. So we have added nonlinearity, which allows us to represent more functions. So we can kind of see for this, what functions can we represent? So looking at this, all the functions that we are able to represent with, all the functions that we are able to represent with 6 should also be possible, plus with some leniency as well, because this is a more complex graph and you are taking in things from multiple nodes. So if we look here, we can see now we are able to do the situation where we kind of have 2 functions. So like h right here, where we have like a 0.5x and a 3x minus 9, because we have 2 nodes in the previous layer. So that means we can input those 2 nodes and then be able to represent them accordingly. So that's why for 8, we can actually do all options except for log of x, which we don't have a distinct way of being able to represent with just the 2 hidden nodes. So that is going to be your solution for it. And yeah, so it kind of shows like the case where you can kind of incorporate different nodes and different neural network architectures and be able to represent different functions. And kind of just bringing it back to the mini lecture where we talked about the universal function approximator. As long as we add more nodes and kind of have 2 layers, then we should be able to represent any functions. And you kind of see that happening just with these subparts, because we started from something in part A, right here, that was a super simple, just 1 node. And from that, we could only represent one of the options. But as we kept adding on, adding multiple layers, adding non-linearities, and adding multiple nodes per layer, we eventually got to be able to represent everything except for the log of x. So option G. Yeah, so that's the end of this discussion worksheet. I hope you enjoyed it, and I hoped you enjoyed taking 188 in general, because this will be kind of our last formal discussion, because the last week of discussion will be more just final review. So yeah, I hope you enjoyed these videos overall, and that you had or will have a nice Thanksgiving break, and just hang on in there. We're almost at the end of the semester.